Open up any modern Agile backlog, and you will find a graveyard of identical, undefined requests. Product managers and stakeholders know they want a high-quality system, so they fill the board with tickets demanding performance and flawless execution. Take this standard user story. The system must be secure, user-friendly, and process data quickly. To an engineer, this ticket is an immediate red flag. It is an engineering failure masquerading as a requirement. Those words are subjective soft goals. You cannot write a unit test for a feeling. A system architecture cannot be optimized for a qualitative state without exact mathematical boundaries. This split-screen visualization shows the inevitable collision of subjective terms. On the left, a product manager writes fast, expecting an API response time of 100 milliseconds. On the right, an architect reads fast and provisions a database returning queries in 1,000 milliseconds. That 900 millisecond expectation gap is where rework happens. It triggers fractured code bases and structural failures the moment the application faces real-world traffic. The software industry has historically thrown all of these vague abstractions into a single dumping ground, the non-functional requirement, or NFR. Achieving high system quality requires engineering teams to move past the NFR bucket. The path to a stable architecture demands replacing subjective adjectives with rigid, quantifiable metrics. The International Requirements Engineering Board, the IREB, recognizes the danger of this ambiguity. They explicitly recommend abolishing the term non-functional requirement from the engineering vocabulary. Requirements split into two categories. First, constraints, represented by a steel box. Second, quality requirements, a tunable dial. The box expands into product, like legacy databases or memory caps bounding the solution. And process, hard deadlines, compliance, or pipeline tools dictating the build environment. The defining trait of a constraint is its rigidity. It permits no negotiation. If a system is perfectly designed but violates a constraint, it fails to meet the business or legal needs of the project. Quality requirements serve a different function. They act as the dial. While a functional requirement tells the system what to do, a quality requirement dictates how well the system must perform that function under specific conditions. Quality requirements force architects to navigate trade-offs. If you maximize security by requiring heavy, multi-layered encryption, you will see a corresponding increase in performance latency. You cannot maximize every dial simultaneously. When teams confuse non-negotiable boundaries with negotiable trade-offs, the resulting architecture is often built on contradictory assumptions. Stakeholders often carry implicit requirements, things they assume the system will handle but never explicitly state. If you only ask what matters, they will rarely mention maintainability or portability until those factors become problems. To catch those gaps, engineers rely on the ISO 25010 standard. This 9-panel grid acts as a technical safety net, providing characteristics that must be evaluated to ensure technical completeness. Rather than relying on simple speed metrics, the framework forces architects to measure efficiency by tracking resource utilization under heavy load. The 2023 update also accounts for modern risks. It isolates safety to protect against failures where software malfunctions lead to physical harm or massive asset loss. The ISO framework ensures technical rigor, but misses the human and legal context of the real world. The Volere template provides the business counterpart. Chapters 10 through 17 catch these human elements, from cultural boundaries to strict legal obligations. Volere elevates legal compliance to a core structural concern. It forces the team to build mechanisms for regulations like GDPR directly into the data architecture on day one. It also maps out accessibility and cultural needs. It translates regional data formatting and inclusivity into hard limits that the UI components must respect. Integrating the technical rigor of ISO with the business context of Volere identifies critical architectural limits that are usually missed in a standard requirements gathering session. Identifying requirements is the first step. To make them actionable, they must be translated into deterministic, testable logic. Architects use the Architecture Trade-off Analysis method, or ATAM, to bridge this gap between a wish and a specification. ATAM utilizes a 6-node quality tree scenario. It replaces vague goals with a chronological flow of events. Let's map a performance requirement. First, we define the source. This identifies who or what is driving the action, such as external users hitting the network. Next is the stimulus. This is the exact event occurring, like 1,000 transactions per second hitting the search API. We then define the environment. Here, the infrastructure is already under stress from a Black Friday peak load, sitting at 80% CPU utilization. We isolate the target artifact. We are observing the Elasticsearch microservice, not the entire system. We map the required architectural response. The service must check the cache first, perform an index scan if it misses, and throttle traffic if resources deplete. Finally, we set the fit criterion. This is the mathematical boundary for success. In this case, the 95th percentile of response times, the P95 metric, must remain under 200 milliseconds. This exact statistical distribution is mandatory. An average response time of 200 milliseconds can hide severe lag spikes. The P95 metric proves consistent stability for the vast majority of users. This 6-part scenario transforms an abstract wish into a deterministic test case that any developer or QA tester can verify. The final goal is operationalization, the engineering practice of converting qualitative soft goals into functional, hard-coded realities. Look at this comparison. The top half shows a vague backlog ticket, keep data safe from hackers. The bottom half shows the operationalized hard goal. The hard goal dictates that data at rest is encrypted using the AES 256 GCM algorithm, and all access is verified through role-based access control. You cannot audit a feeling of safety, but you can verify a cryptographic standard. The same applies to maintainability. Asking for clean code is a request for an opinion. The operationalized goal requires zero modification to the core domain for new plugins and a strict 80% branch coverage score. This binds the developer to a strict interface boundary. If the code requires modifying the core domain to add a feature, the build pipeline fails. Operationalizing these goals removes subjectivity from the QA process. There are no disputes over whether the software is fast enough or safe enough, because the metrics decide the outcome. This engineering workflow provides the blueprint. Classify via IREB, frame context through ISO and Volere, and operationalize results into ATAM scenarios. The structural integrity of a software system is built on the clarity of its constraints. Replacing subjective goals with precise engineering specifications allows a team to move from architecture to production without the rework that ambiguity creates.